delayed now. Oh.
The half wave rectifier? Just the half wave. Full wave? Half wave.
It's like you're high-fiving yourself over and over and over again.
But with lag, so you always miss it.
Just like the most narcissism ever. You're great. High five.
I did that all the time when I was a kid in like the mirrors that you can adjust. I always adjusted.
Oh man. Okay, so great. Lecture 3.2, zeroth order measurement systems. So we, as you might recall, we talked about the different models in the first lecture, right? We had input-output ordinary differential equation model, mathematical model. We had the transfer function, and then we had the frequency response function. Those were our three mathematical models, and then we also introduced the block diagram as well. Now, those could be nth order, right? So the input-output differential equation could be of order n. The transfer function could have a polynomial on the left-hand side with, or in the denominator that's order n, so it could be any order. But we're going to focus in this class on 0, first, and second order systems. And fortunately, the characteristics of 0, first, and second order systems show up as sort of components of higher order systems. So you see first and second order characteristics in third and fourth and fifth order systems as well. So it's useful not just because it's easier, but because these concepts actually just get repeated again and again at higher orders. So when we're also doing first and second order and zeroth order systems, because most measurement systems can be approximated by them. Second order is usually the highest order that we need to go to for most measurement systems. Some of them will get more complicated than that, but we needn't fear, and we would still be able to do it if it went higher. But we're just going to take a little bit of time to discuss these lower order systems first. So, zeroth order measurement systems. In special cases, we can consider measurement systems to be modeled by zeroth order, air quotes here, differential equations. That is, algebraic systems. If both input u and output y are static, the time derivatives of equation 3.1, which is the input-output ordinary differential equation with all those derivatives on the input and all those derivatives on the output, remember that? All of those derivatives are 0. This leaves the input-output equation with some constant k in this form. So the output is just some constant times the input. It's my kind of measurement system. We call k the static sensitivity. Okay, you guys got introduced to that term in chapter 1, and so this is another, not when we talked about it in class, because we didn't talk about chapter 1, but you guys read the textbook, of course. Technically, the input needn't be static, but but one would question the efficacy of a measurement system that has a dynamic input and a static output. I mean, I don't know about you guys, but I feel like that would be a bad measurement system. If it's like changing, if the input in these measurement systems is the measurand, right? It's what we want to measure. So if it's changing and our measurement system's not changing, pretty bad measurement system. Might want to go back to the drawing board on that one.
This board is 4 feet. This board is also 4 feet.
Right. Exactly. It's it's maybe, I guess, what do they say? Even clocks are right twice a day. Even broken clocks are right twice a day.
Broken clocks right twice a day.
Yeah. So, okay. Good. So, in fact, we have assumed neither input nor output changes. This can be approximately true if we calibrate and measure only in steady state. Okay? So nothing's changing. The input's not changing, the output's not changing, everything is steady. Another way to have equation 3.8, this just linear relationship, as our model, is if we assume there are no energy storage or dissipative elements. This type of measurement system does not exist, but in certain situations it can be considered approximately valid. Much more frequently we will say the zeroth order model works for a measurement system because we're going to just consider steady state situation. So nothing's changing, the input's not changing, the output's not changing, we wait until everything is nice and steady, and then there's just a gain between the input and the output. And if the input, the measure and changed at all, then we have to wait until it's steady again, the output's steady again before we took the measurement. Otherwise we wouldn't expect this equation to hold at all. Okay? Good. So now we can do an example. Explain conditions under which the following systems can be considered zeroth order. So a bulb thermometer.
Sitting in an ice bag. Oh.
Yeah.
Thermal equilibrium with its surroundings.
Yeah, so if it's in steady state, then if it's not changing, if the temperature that it's measuring isn't changing, and it is at the same temperature as its environment that it's trying to measure, then I think that this model should work okay. As long as you calibrate it in steady state only, and you take measurements in steady state only. So, whoa.
Well, doesn't that kind of, I guess, in a way defeat the purpose of having a thermometer then? Because a thermometer you should be able to read off
Well, that's why
if it changes quickly.
we don't use zeroth order.
Right.
It's
Well,
not useful. It's just.
It's not bad if you're willing to wait, right? If you're like, okay, I don't mind if I put my thermometer in some place. I know that it's not really zeroth order, because if it's zeroth order in reality, then whatever the environment's doing, it would immediately have the value of its environment. But it doesn't, right? We know that when we put the thermometer in our mouth or whatever, or we are any thermal system we're familiar with, takes a while to change, right? In your house, to heat up the house. It takes a while, and so your thermal system that is your bulb thermometer is going to take some time to respond. But if you're willing to wait and always consider it only when it's in steady state, and then if it's going to change, you're going to wait for the next steady state to arise. You could come up with a zeroth order model for a bulb thermometer, as long as you're willing to just always only consider steady state. So say you were measuring 70 degrees, and then the temperature changed, and it's like heads towards 80 degrees. Well, your model wouldn't be valid the whole time it's changing. And then once it's finally steady again, you would say, okay, now it's valid again. So that would be, valid in steady state. That's fine. What about a mass balance?
Talking about like balance scale?
Yeah, like a scale.
The one you'd find in your chemistry lab.
Yeah,
Inside
in
of
your
that,
neighborhood chemistry lab.
Is the taper framework there?
Sorry?
Do you like taper it to make sure that it's at like 0?
Oh yeah. So so to calibrate it, you would need to make sure that you're so we're not so much concerned about calibration here. We're mostly concerned about what model would reflect how this thing responds. So I don't know if you guys have ever done this, but if you guys ever like dropped a small weight on a mass balance and had it react?
Yeah.
Yeah.
Kind of wobbles.
Yeah, it kind of does this, right?
So then the ideal would then be if you were to place a 20-gram weight on mass balance, it would show 20.
It would immediately be at
It would be it's
the
it's
other
like when you're
new
stepping on
value.
one of those old gym scales, you know, you go weigh yourself to find your body fat percentage. It's like has a tendency to wobble. You're trying to adjust it. Like there would be just instant.
Yeah, it would just instantly be at the value. The readout would be there. Of course, so of course it's not valid all the time. The zeroth order is not going to be valid for this in the transient at least, right? I mean that's pretty clear. But it is valid if we are going to consider just steady state. If we're willing to wait for this thing just to be a steady state, we could come up with a zeroth order model that works okay. And that's what we do with these mass balances, and that's what we do with bulb thermometers too. We don't expect that it's going to be right when we change it for a while, right? We expect that it's going to be wrong for however long, few seconds, few minutes, and then it's going to slowly be right. And that's so once again valid in steady state. What about a speedometer?
If you went from 0 to 60
Like,
instantly.
I feel like it has something to do with steady state again.
Yeah, well, I mean, it's
Cruise control.
If you were on a flat road with the cruise control on, with the speed not changing at all,
right.
then the speedometer reading would be valid.
Yeah,
And accurate.
and that's
And then
the.
no air resistance.
I think it kind of highlights something about this, and that is that
There's a-
the model that we choose depends on what we're interested in, right? Like, so with the speedometer, we kind of want to know, like, as we're changing speeds, what speed we're going, right? We don't want to have to wait.
It's helpful.
Yeah, you don't want to find out 30 minutes down the road.
Right.
Like, oh, hey,
You
I'm
know how
going
fast
60
you were
the
going?
entire time.
No, I have really no idea.
Wait, we're about to find out. Oh, yeah, you got me.
Zeroth or this would only work. This actually works for the cops. So they can instantly tell you, yeah, you were going 75. Dang it.
Yeah, no, that's, for them, clearly they're going to want to have a very quickly responding measurement system. Zeroth order would be ideal, but of course it's not in reality zeroth order.
But they can get mighty close.
Yeah, they're using things that move pretty fast. The radars.
Is it? I thought they always use. They use radar, but they also use laser light, right?
They might now. I don't know. Probably.
Like how fast? It's the same principle using like radar or sonar. How fast it bounces back. They use light.
LiDAR. It's actually what it's called. Yeah.
Seriously?
Yeah. This is mostly invalid. Yeah, so you can get the laser rangefinders. Yeah, there's like nowadays there's like 50 different devices for each thing you want to do.
Because they can determine based off the time it takes for it to this signal to go to and from, right, how far it was from.
And if you look through them for long enough, then you actually, because it's been going at the speed of light, you actually age slower.
What?
That I just
Yeah.
I just made that up.
And then you end up on the same planet as Anne Hathaway and stuff.
You are stuck.
What?
Remember Anne Hathaway gets stuck on that planet?
Hold up, there was a time on that.
I
put 10 rank
Just
hydros
go with
in a row.
Just
and
go
I'd
with
go,
the
"Sure."
Do we have any questions on zeroth order systems?
I think we're good.
Okay.
Pretty simple.
Zeroth order.